Hey, astronomy students, this is Mr. Brennan, and I've got an activity here that I'm hoping will help you make some sense about the idea of an expanding universe. We're going to take an example, sort of a made-up story about a bike race, and as it says at the top there, we can imagine that the riders left the starting gate at the same time, but some time ago, and that they're wearing radio headsets so that they can be in touch with the race organizers. At a certain point, the organizers radio a message to the riders and say, okay, please tell us how far you've traveled and what your velocity is. How fast are you going? So the riders go right ahead and they report out of how far away they are from the starting gate and what their velocity is. So this rider right here reports out that she is, say, 72 miles away from the starting gate, and that her velocity, as we read over here, looks like it's something like 24 miles per hour. And everybody reports back on their progress, and it's not that alarming or interesting to note that the fastest riders, the ones that have the highest velocity, go the furthest distance in that amount of time. So, that's not too surprising, and it's worth thinking about this poor rider right here at the origin who radios back in and says, well, I'm 0 miles away and I'm going 0 miles an hour. So maybe that's a rider who, excuse me, when the starting pistol went off, their bike broke or they fell over and they injured themselves. So that's what's going on with these riders. We have this linear velocity versus distance graph. Okay, so now that we know what this graph sort of represents and how the data points were collected, here's one thing that is helpful to think about. Okay, as it says at the bottom there, at the beginning of the race, all the riders were, of course, at the origin. They were 0 distance away from the start, and they were traveling at 0 miles per hour. So they're at the coordinate 0, 0. But now, excuse me. But now, sometime later, the riders have obviously separated, and this velocity versus distance graph, velocity on the y-axis and distance on the x-axis, captures the idea that the riders are, of course, spreading out. And recently, we've been thinking about galaxies in our universe. A little typo there. 2 typos. Galaxies in a universe. We might say that if this data were collected about galaxies, we might say that the distance between the galaxies was growing over time, or perhaps we would even say that the universe that these galaxies were in was expanding. In other words, at a certain moment in time, the universe is, say, 72 miles wide, covering all the galaxies from the origin out to the 72-mile mark. And of course, if we had shown this graph at an earlier time, the riders would not have gotten as far. Maybe we would check in and find out that the bikers had only traveled 30 or 40 miles, and the bike universe is only 30 or 40 miles big. So this is a little bit of a roundabout way of saying that this data by itself is sort of great evidence that if this were information about galaxies, that the universe these galaxies were in would be an expanding universe. We're going to do something more with this in just a moment. So let's see if we can extract something else out of this graph, which would be very meaningful. And the title of the graph that I put in a box now says, when did the race begin? And is the information on this page enough to establish when this race began? So let's think about some of the data points. Let's take a look at this one here. It's a particularly obvious data point right here, the next to fastest rider. Okay, they radio in, they say, hey, I'm 60 miles away and my velocity is 20 miles an hour. So if we make the reasonable assumption that the biker has sort of been averaging 20 miles an hour, that at this moment they're kind of traveling at their average rate, then 20 miles an hour and 60 miles of difference would imply that the rider has been riding for 3 hours. Okay, and if we check out the next data point, we can estimate this to be 48 miles and 16 miles an hour. And again, that would imply that that rider has been riding for 3 hours. So it's a fair race. Everybody started at the same time, or at least those two riders started at the same time. Let's check another one. What about this one here? This third data point up. Okay, 24 miles is the distance, and the velocity is 8 miles an hour. So again, 8 miles an hour. They're now 24 miles away. We can assume, if that's their average velocity of 8, that they've been traveling for 3 hours. So when did the race begin? The race began 3 years ago. All right. Well, if these were galaxies and we could do a similar kind of calculation, then we'd have some really intriguing information. If we could look at galaxies as velocity versus distance and plot their characteristics, and if we got anything close to a linear relationship like Edwin Hubble did, then we could do a similar kind of thought experiment, and we could say how long, not how long the race was, but how long have the galaxies been separating from one another. In other words, how long have galaxies been expanding in space? Or should I say, how long has the universe been expanding? We could tell how old the universe is by looking at this data. So let's figure out one last trick to do, and how you can apply this to some wonderful Hubble graphs that show velocity versus distance. So as you see, I've drawn a dotted line through those data points, and they're perfectly lined up. But even if the data was kind of noisy and erratic, we could draw a best fit line, an eyeballed best fit line. We can of course get the slope of that, and if we go ahead and get the slope of that line, let's try this here. Okay, here we go. Let's say that we pick this point, all right, out to here, and we picked, oops, let me click there, and then this point here, all right. And so we've got two data points right here and right there, and we can get the change in y divided by the change in x. And so what's our change in y? Well, 20 is the height of this, right? So our change in y is 20 miles per hour, and our change in x is, well, we go from 0 out to 60, so it's 60 miles, okay? And then we go ahead and calculate the change in y over the change in x, 20 divided by 60, which is of course 1/3. And we'll leave the units off just for a moment. Now, that's our slope. Our slope of our line is 1/3. So as a quick summary of what we've just done, we found that the slope of the best fit line was 1/3. We found that the time of the race was 3 hours. These are, in fact, inverses of one another, 3 and 1/3, and that is absolutely not a coincidence. In fact, that's going to happen every time, as long as the units work out properly. Sometimes we'll have to play around with units a little bit, but in this particular case we won't, and for the foreseeable future we won't have to deal with any kind of correction. So here's a general strategy for determining the age of a universe, which is remarkable that we can do this. First of all, make a graph of velocity versus distance for galaxies in that universe. Plot their properties, velocities versus distance, velocity on the y-axis, distance on the x-axis. And plot the points and draw in the best fit line. Just eyeball it. Draw a line that goes through the data as best as possible. Find the slope of that line using 2 points on the line. That's the change in the y value divided by the change in the x value, the rise over the run. And then finally, invert that slope and you'll have the age of the universe. So for example, if you get a slope, sorry, let me do that here. If your slope is equal to 2 divided by 15, then the age of that universe that gave you that data, making up data here, would be 15 divided by 2, or 7.5. Oh, let me move that out of the way. 7.5 billion years old. Okay, so it's amazing that we can say this and not have somebody come and take us away. Okay, that is the way that we can determine the age of a universe. So I'm going to have you try a couple of practice problems on a handout. So you're welcome to look at this again if you'd like, or to repeat sections. But I'm going to ask you to be doing exactly this ABCD process right here. Okay. So good luck, and we'll talk soon. Take care. Bye.